Hi. In the previous example, that is in example 7, we have discussed the convergence of a Fourier series in terms of the interpretation of the so-called Dirichlet kernel converging to an impulse train and thus explaining the convergence behavior of the Fourier series. Okay, so in the context of Fourier series expansions, the convergence discussed in terms of the Dirichlet kernel is an example of pointwise convergence. Now we can clarify this point first by remembering what we mean by the Dirichlet kernel and how we interpret the behavior of the Dirichlet kernel tending to an impulse train and thus explaining the convergence of a Fourier series. But also we have seen that for certain periodic signals, within a period we may have points where the signal is not continuous. We have discontinuities, a jump from a value to another value. So at those points, how can we interpret the convergence of the Fourier series? So the question is the following. Suppose that x of t is a periodic signal with a finite number of discontinuities. Within a period. Okay. For instance, we have x of t and we have the following form. We are going to consider a period, say we consider the interval from minus t0 over 2 to t0 over 2. So this is a period of x of t. And there we will have points where the signal is not continuous. Okay. For instance, at this point and this point, at these 2 points, the signal is not continuous. But x of t is a periodic signal, and we are able to evaluate the Fourier series. So we ask the following question. The Fourier series will converge to the value of x of t at points where x of t is continuous. In fact, we have more than continuity. We assume that the function is smooth in the intervals or subintervals where it is continuous, meaning that we have also some existence conditions related to the derivatives of x of t. We can assume that x of t will have a derivative at points where it is continuous, and also we will have a derivative in the left sense or right sense when we approach to the discontinuity. So we have such smoothness conditions, but these conditions are satisfied by most of the signals. In fact, maybe for the entire set of signals of interest in engineering applications, but signals with discontinuities are very common in signal processing applications. So we ask the question related to the convergence of the Fourier series at the points of discontinuities. Okay, now we are going to answer this question in a not very formal way, but in an intuitive way by means of the Dirichlet kernel interpretation. Now, x of t has the Fourier series representation, k from minus infinity to plus infinity, ak e to jk omega 0 t, and ak is 1 over t0 from, okay, let us consider, for instance, this particular case from minus t0 over 2 to t0 over 2, x of t e to minus jk omega 0 t integrated with respect to t, or let us use the t prime convention, because we are going to substitute this in the expression of the Fourier series and obtain the Dirichlet kernel. So x of t is written as, when we substitute ak in the Fourier series expansion, we have k from minus infinity to plus infinity, 1 over t0, the integral from minus t0 over 2 to t0 over 2, x of t prime e to minus jk omega 0 t prime integrated with respect to t prime. So we have this expression for ak, and we have e to jk omega 0 t. Now, we interchange the two operations, and we obtain from minus t0 over 2 to t0 over 2 x of t prime, and then we have the we have the series k running from minus infinity to plus infinity, 1 over t0 e to jk omega 0 t minus t prime. Okay, this is the t prime. Okay, we obviously recognize this term as the impulse train. This is the Fourier series representation of the impulse train m from minus infinity to plus infinity delta of t minus t prime m t0. Okay, so we have the impulses located at t minus t prime, then we add or subtract integer multiples of t0 to that, and we obtain an impulse train. And that's how we interpreted the action of this expression within the brackets on x of t prime. We sampled the value of x of t prime at t prime equal to t, and we obtain x of t. Now, remember that instead of looking at this problem in this rather direct way, we have the so-called truncated Fourier series. That means we consider only a finite number of terms. So in that case, we have Sn of t, the truncated Fourier series, k from minus n to plus n, ak e to j k omega 0 t. And if we write this down exactly in the form given above, we have the Dirichlet kernel in the integral expression from minus t0 over 2 to t0 over 2 x of t prime. Now here, instead of this series, we have a finite sum running from minus n to plus n, 1 over t0 e to j k omega 0 t minus t prime integrated with respect to t prime. And this term here is called, remember, the Dirichlet kernel, En of t minus t prime. Okay. Now, we have in example 7, in the previous example, we have evaluated the expression of the Dirichlet kernel, and we have seen that it has a main lobe at t, and it has side lobes over the entire domain of the function, which is also a periodic function with the same period, capital T0. And we have interpreted the action of that action of the Dirichlet kernel, or the Dirichlet kernel acts as an approximation for the impulse, and the action as capital N tends to infinity will be similar to the action of, in fact, exactly the same as the action of the impulse. But for larger values of n, the Dirichlet kernel will be an approximate impulse signal. Okay, now we can look at this problem in terms of illustrations to see how we have the convergence phenomenon at the usual point and at the point of discontinuity. The discontinuity case will be, of course, more interesting. So now let us look at this problem. Okay, now just for the sake of illustrating this convergence behavior of the Fourier series, let us choose a signal which has a single discontinuity, just to avoid confusion, a single discontinuity at, for instance, at t equal to 0. So, for simplicity, assume that x of t is discontinuous at t equal to 0. So we have the following graph. We have x of t. Okay, we draw the graph from minus t0 over 2 to t0 over 2 over a period. It will repeat itself periodically with period capital T0. So here the signal will be a smooth function for negative values of t. Then it will have a discontinuity at t equal to 0. And again, it will be smooth over the interval where p takes positive values. So we have only a single discontinuity at t equal to 0. Now okay, and also let us remember the expression of the truncated Fourier series. Sn of t is from minus t0 over 2 to t0 over 2 x of t prime, the Dirichlet kernel evaluated at t minus t prime, and the integration is with respect to t prime. Now the Dirichlet kernel, remember, tends to the impulse train as n tends to infinity and Sn tends to x of t. So limit as n tends to infinity, Sn of t is x of t. But we are considering points which are not equal to 0, because at the discontinuity we are going to have a different argument, and the Dirichlet kernel, the limit as n tends to infinity, dn of t minus t prime is simply the periodic impulse train, delta of t minus t prime minus m t0. Okay, we have t minus t prime, and then the periodic repetition of the impulse with a period t0. Now remember that graphically the Dirichlet kernel has a main lobe which has a large magnitude for larger values of n, and then it has side lobes which are quite negligible for larger values of n. So at a point different from 0, we will have a following picture. For t different from 0, but we are in the interval from minus t0 over 2 to the t0 over 2, we have the following interpretation. Now this is our signal x of t which is discontinuous at t equal to t0, but continuous and very smooth otherwise. So we have this behavior, okay, like this. Now when t is different from 0, for example, let us choose t here. Now let us draw the graph of the Okay, in fact, we are considering the integral expression as n of t. So we have the primed coordinate. Okay, let us, no. Yeah, this is, let us draw this in terms of the prime coordinate, x of t prime. And this is t prime and dn of t minus t prime. So at t, we are going to have a main lobe with a large magnitude, and we will have smaller side lobes. Okay? So, at t, we have the main lobe. Therefore, the integral of Sn of t will be approximately equal to x of t for larger values of n, for large n. That means the Dirichlet kernel will sample the value of x, the signal x of t prime, at t prime equal to t. Now let us look at what happens at t equal to 0. At t equal to 0, we have the following picture. Again, our signal will be, this is t prime and this is x of t prime. We will have from minus t0 over 2 to t0 over 2. So we have a discontinuity at t equal to 0. Now the Dirichlet kernel will be, again, with respect to t prime, we draw the graph of dn of, now t is equal to 0, 0 minus t prime. Okay, so here, this means that we have this main lobe at, okay, I have to draw it more carefully. We have the main lobe at 0, and we have the side lobes. So around 0, the main lobe is, of course, dominant. Now, here we obtain the following intuitive feeling from this graphical representation of the signal and the Dirichlet kernel, it will be clear that, now remember, we multiply the signal with the Dirichlet kernel and integrate. So integration is a summation operation, or finding the area under the curve. So in this case, Sn of 0 will be approximately equal to as n tends to infinity, the main lobe will become larger in magnitude and the side lobes will decrease, and therefore half of the expression related to the Dirichlet kernel will be of importance in calculating the value of Sn of t, which is t equal to 0, Sn of 0, and there half of the area under dn will dominate. So we will have the value of the partial sum will be approximately equal to x of 0 minus plus x of 0 plus divided by 2. Which means that by means of this argument, the Fourier series converges to the arithmetic mean of the values x0 plus and x of 0 plus and x of 0 minus. That means the value of the signal at a value of t slightly less than 0 and slightly greater than 0. At those points, the function is evaluated, and we evaluate the sum of these values and divide by 2. That means the arithmetic mean. So at discontinuity points, the Fourier series converges to the arithmetic mean of the values of the signal when you approach the discontinuity from right and from left. This is a rather intuitive argument. Of course, the rigorous proof must also consider some issues of smoothness. That means conditions related to the derivative of x of t, the right and left derivatives at discontinuities. So we omit that discussion, but otherwise this is an explanation why the Fourier series converges to the arithmetic mean of the values of the left and right values of the signal at the discontinuity. Okay, thanks for watching.